Hello everyone, I hope that you will be fine. Today we are starting a new topic from our A levels physics. So, the topic which we will be discussing today is circular motion or the motion in circle. So, the learning objective of today's topic will include define the radian and express the angular displacement in radians, understand and use the concept of angular speed, recall and use the equation omega equals to 2 pi over t and v equals to r omega. So first starting with the definition of a circular motion. So circular motion as we know is the movement of the object while it is rotating along a circular path. Some of the examples from our daily life includes drilling a stone tied to a string, washing the clothes in the washing machine, or the clothes which are being dried in a dryer. So the clothes are doing a circular motion. The old fashioned swings that are present in the parks, and the bike, a motorcycle, or some type of vehicle which is moving along the curved path. So if we look at a curved path, so the curved path is a part of a circle. So we can say that anything which is moving in a curved path, although if it is not a complete circle, that is also a type of a circular motion because curved path is a part of a circular motion. Now, one of the most common example of a circular motion that we have in our schools or at our home is a clock. Now, as we know that our clock has three different type of hands. For example, a hour hand that is telling you that how many hours have passed, the minute hand, and the second hand. So, in this picture, the red one is basically the second hand, and of course, as it is rotating in a circular manner, the seconds are being passed, and we know that these or this much amount of the seconds has been passed as it is doing its rotation in the clock. So if we talk about the circular motion of this second hand, so we know that if this second hand is going to do a complete 360 motion, which is equivalent to one complete rotation or completing one complete cycle or completing one complete revolution, then of course 360 degrees of this revolution will be equal to 60 seconds. Why? Because we know that the second hand do its complete 360 motion, and after that we can say that 1 minute has passed, and 1 minute is equal to 60 seconds. So it is doing this type of a motion, and we can compare it to a circular motion like we can see in this diagram that as the object moves in a circular path, it is covering some linear distance that is represented by s, whereas some type of the angle is being swept away while the object is doing a circular motion. The distance from the center to the outermost part of the circle is the radius of the circle. Now we can say that the second hand takes 60 minutes or 1 minute for one complete circle as we just discussed. So that means that 60 seconds will be equal to one complete revolution, and one complete revolution is equivalent to 360 degrees. That 360 degrees uh, are swept away that when one complete revolution is completed by the clock hand. So we can say that 1 second is equal to 360 degrees divided by 60. So for 1 second, we can find out that how many degrees has been swept away. So if the second hand of the clock is sweeping away the angle of 6 degrees, that means that 1 second has passed. Similarly, if it is sweeping away the angle of 12 degrees, so 2 seconds have passed. 18 degrees have swept, which means that 3 seconds have passed. 24 degrees have swept by the second hand in a clock, that will means that 4 seconds have passed. So 1 second will be equal to 6 degree for the second hand of the clock. Now we can compare this with the circular motion in our daily life. That let's suppose if the object is doing a circular motion like shown in the second picture, it is moving the angular displacement, the angular distance or displacement, that is represented by s. The theta here, which is the angle, will be known as the angular displacement that is covered by the object, and r is the radius of the circle. So what is angular displacement? The angular displacement is given by units, degrees and radians. So as we have just discussed in our previous slide, that as the object is moving in a circular path, so some amount of the angle is being swept, and that angle which the object is sweeping is known as angular displacement. So there are two types of displacement. One is the linear displacement, that the object is covering along the circumference of the circle, and the other one is the angular displacement, that is the angle which is being swept away while the object is moving this linear displacement. So we'll try to understand by this picture that let's suppose there's an object which is moving in this circle as shown in the picture. So P is representing the initial position of the object. And after some time, let's suppose some time has passed, so delta t has passed, the time equivalent to delta t has passed, and the object while moving along the circumference, it has covered a displacement, a linear displacement of s, represented by s, and it has reached its new position, that is p1. So the object have moved from p to p1 along the circumference of the circle, and while doing so it has covered a linear displacement of s, where this angle theta will be representing the angular displacement of the object. So this theta, that is the angle, is basically the angular displacement covered by the object. So from here we can write the formula that the angular displacement theta will be equals to s over r. S is the distance covered, the linear distance or the displacement covered by the object. R is the radius. So angular displacement is given by the formula theta equals to s over r. And if you look at this diagram here, this segment is showing that s is basically the arc length of the segment. So as you have learned in mathematics, that arc length is the outer distance or the circumference which is moved by the object in while moving in a circular path. So here s is the arc length of the circle. Okay, so here you can see another picture, that let's suppose we have the example of this person which is lifting some mass, and while lifting, of course, he is moving his hand in a circular manner. Why? Because the elbow is acting like a pivot point, and around that pivot point the hand is doing a partial circular motion. So here the linear displacement is the arc length which is moved by the object, represented by s. Theta is the angular displacement, and r is the distance from his elbow to the mass which is kept in his hand. So in simple words, the angular displacement of the object is the distance traveled by it around the circumference of the circle divided by the radius. So angles in radian. So as we know that the angle is always measured in degrees. But if we want to measure the angle in radian, so we can use the formula that angle in radian equals to arc length divided by the radius of the circle. So as this is the same type of a picture, s is representing the arc length of this shaded segment, and theta is representing the angular displacement, which will be in radian, and r is the radius of the object. So as you can see in the picture that it's written that since for the full circle the s, that is the arc length, will be equal to the circumference of the circle. If the object is doing a complete circle in this circular path, which is equal to one complete revolution, then he is moving along the circumference, and the formula for the circumference is 2 pi r. So here the arc length will be equal to the circumference of the circle. Okay, so from here we can do some calculations. For one complete circle, the circumference is given by 2 pi r, where r is the radius. The angle in radian will be given by arc length over radius. So of course the arc length is equal to the circumference 2 pi r divided by radius, that is represented by r. So radius will be cancelled out because one of the r is in numerator and the other is in denominator, and we will be left with 2 pi radian. So from here we can say that 360 degree is equal to 2 pi radian. Okay, so here we can do the conversion, that let's suppose we want to convert the degrees into radian or radian into degree. Okay, so here 1 radian will be equals to 57.3 degrees. Okay, that let's suppose if the object is sweeping away the angle 57.3 degrees, we will say that 1 radian of the angular displacement has been covered by the object while moving in a circular path. Okay, so these are some of the comparison, and we are comparing the degrees with radian, that how we can convert from degree to radian or radian to degree. So 2 pi radian will be written as equal to 360 degree. So from here the same formula, so pi radian will be equals to 180 degree. And similarly, if you want to convert the degrees to radian and you want the answer in the radian, so what you are going to do is that you are going to multiply pi over 180 with your answer, with your number in degrees. Okay, so how do we define 1 radian? So 1 radian is defined as the angle subtended at the center of the circle by an arc of length equal to the radius of the circle. Now what does that mean? So look at this picture. As you can see that the arc length of this shaded segment is equal to r, whereas the radius of this circle is also equal to r. So if the arc length or the linear displacement covered by the object is equal to the radius of the object, then we say that the angular displacement is 1 radian. Okay, so that's how we define 1 radian, that 1 radian is defined as the angle sustained at the center of the circle by an arc of length equal to the radius of the circle. That if the arc length become equals to the radius of the circle, then we say that the angle sustained is equal to 1 radian. Now we have simple question here, one of the question problem, so that we can understand that how we can do the conversion. For example, if the theta, the angle is given to as 60 degree, so you need to find the answer in radian. So here we need to do the conversion from degrees to radian. So the angle theta is 60, and we know that 360 degree is equivalent to 2 pi radian, as we have just uh, understood in our previous slide. Therefore, if we need to convert 60 degrees to radian, what we are going to do is that we are going to multiply 60 degrees by 2 pi over 360. Okay, so while we do so, we do this by using, let's suppose, calculator, and after doing the calculation we get the answer 1.05 radian. So what does that mean? This means that 60 degree is equivalent to 1.05 radian. Now we can do some more examples. Let's suppose if I give you or in the paper it's given to you that the angle is 90 degrees and you need to convert this angle in from degrees to radian. So what is it in radian? Okay, so you need to change this angle from degrees to radian. So what you are going to do, you are going to use the same formula, that 90 degree multiply by 2 pi over 360. Okay, so either you can multiply it by 2 pi over 360, or either you can multiply it by pi over 180, because it's the same. Because let's suppose if I cancel out 2 by 360, it becomes equal to 90 multiplied by pi over 180. Okay, so either you multiply your angle with 2 pi over 360, or either you multiply your angle with pi over 180, it is going to give you the same answer. Okay, so let's suppose for here pi we know is equal to 3.14 and 180 is divided by it. So let's do the calculation with our calculator. So 90 multiplied by 3.14 divided by 180, it will be equal to 1.57 radian. Okay, so from here we have understood that 90 degree will be equal to 1.57 radian when it is converted from degrees to radian. Okay, so you can do the same with the other one. For example, the next question is convert the following angles from degree into radian. So you can convert 30 degrees from degree to radian by using the same method, and convert 105 degrees from degrees to radian by same method by multiplying 105 with 2 pi over 360. Okay, so now talking about the motion in the circle. So let's suppose we have this example that we want to discuss, that there's an object which is doing a circular motion. Like we can see that the girl is railing this object into the circular path. So if the girl is moving this object with a uniform speed, okay, or a uniform motion, so the question arises here is that will the object have a uniform velocity in this circular path? The answer is no. The speed of the object in a uniform circular motion is constant, but the object velocity change in the direction of the motion, therefore there is an acceleration. Now any object which is moving in a circular path, it might have a constant speed, but it cannot have a constant velocity, because we know that speed is a scalar quantity. It depends upon the magnitude only, whereas the velocity is a vector quantity. It has a magnitude plus direction. Okay, so even if the velocity is having a constant magnitude, but of course if it is moving in a circular path, it will have different velocity direction. Okay, now let me explain it to you. Let's suppose the object is moving in this circular path like this. If the object is here at this position, okay, the direction of its velocity is in this direction, because velocity is always tangent to the circle. Okay, and after some time when the object is going to reach this point, the direction of the velocity is going to change in this direction, because because the velocity always remain tangent to the circle. The velocity does not have the same direction in the circular motion. And again the object reaches this point, the direction of the velocity becomes like this, tangent to the circle. And again the object reaches another point in the circle, the direction of the velocity again changes to this direction. So from here we can see that velocity depends upon the magnitude, that is the speed, plus direction. So even if the speed is constant, but the direction is not constant. The direction is changing at every single point in the circle. So we say that the velocity of the object in the circular motion can never be constant. And if the velocity can never be constant, so of course we know the changing velocity per unit time is equal to acceleration. So we can say that the object is accelerating while it is moving in a circular path. We are going to discuss the acceleration in our next topic in our next video, but for this video we will not be going in the detail. Okay, so just to understand that why the objects have a different direction of the velocity, we are going to do a simple example. We are going to understand with the help of a single simple example. For example, that which direction would the ball will go if the string is cut. Let's suppose if this is a ball which is whirling, which is doing a rotatory or a circulatory motion like this. Let's suppose if the string is cut or the string breaks while the object is doing this circular motion. So what do you think? What will be the direction of the velocity? We have three options: A, B, and C. Of course, if the string is cut, the object is going to move in the direction of B. So if the object is moving in the direction of B, so we can say that the direction of the velocity is in the direction of B. Okay, that is tangent to the circle. So the velocity direction is always tangent to the circle, and the force is always towards the center of the circle. We are going to study about this force, the centripetal force, and this velocity in our next video. But today we are just talking about the angular displacement and angular speed. So let's discuss the angular speed. That what is the angular speed? So as you can see in the picture here, let's suppose this object is moving in a circular path like this. So while moving in the circular path, v is the angular, it's the linear velocity or the linear speed of the object, whereas the omega is the angular speed of the object. And the relation between the linear speed and the angular speed is given by v equals to omega r. So from here we can see that the angular speed depends upon the radius of the circle. Okay, so what is the angular speed? The angular speed of the body in a circular motion is defined as the rate of the change of the angular displacement with respect to time. The angular speed is the scalar quantity and measured in radian per second. So as we write the formula for linear speed, v equals to distance divided by time. So similarly for angular speed, we have angular displacement divided by time. Okay, so the distance, the difference between the linear speed and the angular speed is that for the angular speed, instead of using displacement divided by time, we use the angular displacement divided by time. And here in this formula, we know that the theta is representing the angular displacement and delta t is representing the change of time. So rate of change of displacement is known as the angular speed of the object. So here w is basically representing the omega, and it is given in the unit radian per second. Why radian per second? Because the angular displacement here has a unit radian and time has a unit of second. So for omega, for angular speed, the unit will be radian per second. Now if we are comparing the linear motion with the rotational motion, we know that for the linear motion, the distance is given by s, the velocity is or the speed is given by v, and time is given by t. But for the rotational motion, this distance or the displacement is known as the angular displacement, that is given by theta, and the speed in the rotational motion is known as angular speed, which is given by omega, and of course the time t is same for both of them. So from here we write the formula that angular speed equals to angular displacement divided by time taken. So omega equals to delta theta divided by delta t. The time to make one revolution is referred to as time period. So let's suppose if the object is doing one complete revolution in a circle, that is completing one complete circumference around the circle, the time taken for that one complete revolution is known as the time period. So the angle through which the object move in one revolution is equal to 2 pi radian. Okay, so we have learned that 360 equals to 2 pi radian. So if the object is doing a complete circle, that is equivalent to 360 degree, that is equal to 2 pi radian. So substituting in the equation, if the object is doing a complete circle, instead of angular displacement theta, we substitute the value 2 pi radian, and instead of time delta t, we replace it by time period capital T. Okay, so here we get the equation that omega equals to 2 pi over t, capital T. Okay, so looking at the relation between speed and angular speed. So speed is given by v, the angular speed is given by omega, and radius is given by r. So we can write that speed equals to angular speed multiplied by radius, v equals to omega r. Okay, so from here if you look at this picture, this object doing a linear moving in a circular motion have a linear speed and it have a different angular speed. So of course if the radius will be different, then the object will have a different angular speed. Okay, so angular speed will depend upon the radius of the circle. The angular speed is inversely proportional to the radius. If the radius is bigger, then the angular speed will be smaller. If the radius is smaller, then the angular speed will be bigger. Okay, so let's try this problem. A toy train traveling around the circular track of radius 2.5 meter in a time of 40 seconds. What is the speed? So if we need to find the speed, we know that speed is given by omega into r. But first we need to find the omega, that is the angular speed. So angular speed can be found by formula 2 pi divided by the time period. So here the time period is 40 seconds. So 2 pi divided by 40 will give us 0.157 radian. So once we get the angular speed, we substitute it in the formula v equals to omega r. So v will be equals to 0.157 multiplied by 2.5, that will be equals to 0.39 meters per second. So that's all from today's lecture, and in our next class we are going to discuss the circular motion in terms of acceleration and the centripetal force, and we are going to derive the relation for the acceleration and the centripetal force in terms of linear speed and in terms of the angular speed as well. Thank you so much.